Hi class, today we're going to be talking about one-to-one functions and inverse functions. And before we talk about one-to-one functions, I just want to recall what a real function is and how that relates to a relation and how they're different. For this first example, I have a relation defined between a and the elements 1 and 2. And this is not a function because my input a is going to two different outputs, 1 and 2. Because my input has more than one output, this is not a function. For this next example, it might be tempting to say that this is not a function as well. However, my arrows are depicting a function because each input has exactly one output. For example, you can see that the input of A has the output of 1, the input of B has the output of 3, and the input of C has the output of 3 as well. But each input has only one output. Because this is a well-defined function, we can therefore ask you what is f of A, what is f of B, and what is f of C, and you should know the answers to that. So there's our function f. You can see that we know the output based on whatever input is in our function. If I ask this question in a slightly odd way though, if I say, what input gives me the output of 1, that's fairly easy to answer with this diagram that we have. That answer would be A. But if I asked you, what input gives me an output of 3, well, I actually have two choices. It might be B and it might be C. And we have options here. So while this is a function, this is not a function that I can answer the question in reverse. If I'm given the input, I know what the output is. But if I know the output, that doesn't necessarily guarantee that I know what the input is. The big question is, are there times when I would be able to guarantee what the input is if I was told what the output is? Let's look at the relationship defined by G. If you notice, I have three inputs, A, B, and C, and each of my inputs is pointing to exactly to one output, so we can call this relation a function. And this G function, we happen to notice that each output also has exactly one input. So I could ask the question a regular way by saying, what is G of A? And hopefully you know what that answer is. But I could also ask the question in a different manner. I could say, what input when plugged into G gives me the output of 3? And with a function like this, if there's only one input going to the output of 3, then we should know that the input is B. And the ability to answer a question like this is because the G function is one-to-one. That means that it is a function and the inputs have exactly one output and the outputs have exactly one input. Notice because each output corresponds to exactly one input, I could ask the question, G of what number gives me 1? And you, for certainty, could say, well, that is G of C. That's an awkward way of writing that question, though. So we're going to go into how to better ask that question. The question asks us to determine whether this function is one-to-one. And one of the things we want to look at is the inputs and the outputs. Now it looks like a jumble of parentheses and braces, but notice that the parentheses all stand for coordinate pairs separated by commas, and then the braces hold 4 coordinate pairs together. So that's where some of the notation is really important. If we didn't distinguish between our parentheses and our braces, this wouldn't quite make as much sense to us. We have 4 ordered pairs here, and what we should notice is that for my ordered pairs, each of those inputs refers to exactly one of those outputs, and If we wanted to, we could draw out the mapping that we did last time, but we would see that there is only one arrow going to each of those outputs. So this is one-to-one. For question number 2, the question's the same. Determine if this function is one-to-one. Let's go ahead and map this out. Notice that 1 is related to 2, 2 is related to 8, 3 is related to 18, and 4 is related to 8. Is this a function? Yes, because each of the inputs has only one output coming out of it. Is this a one-to-one function? Well, our 8 is an output that has 2 inputs pointing at it, both the 2 and the 4. So this is not a one-to-one function. Keep in mind that we're looking at the y values to see if any of them are repeated, and if they're repeated, we want to make sure that they come from the same input. But if they're not from the same input, then it's not a one-to-one function. Recall that if we had a graph, we could check to see if it was a function by doing a vertical line test. The vertical line test would check to see if each input had only one output. Likewise, if I want to check if something is a one-to-one function, then I can do the horizontal line test, and I can check if each output has one input. So when I look at the first example, it passes the horizontal line test because each horizontal line only intersects the graph once. So that would be a one-to-one function. But when I look at the second example, I can draw one line and I can tell you that this horizontal line intersects this graph twice. So this graph is not a one-to-one function. So that horizontal line test is an easy visual way to determine if a graph is one-to-one or not. Let's go back to the image we had of a function and a one-to-one function. In order for this to be a one-to-one function, we have to have each input having exactly one output and each output having exactly one input. One of the ways that we can map this is with this f function that I have pictured here. And if I know that this f function is one-to-one, then that means it has an inverse function. And the inverse function would be defined with the arrows going the opposite direction. That is, the 1, 2, and 3 now become our inputs, and the a, b, and c become our outputs. We would write the inverse function as f to the, it looks like a power of -1. It's not a power, but that's f inverse. And so we say f inverse of 1 would be a, because that's where f of a is 1. And so the reverse would be true. F inverse of 2 is b, and f inverse of 3 is c. Notice that all my inputs and my outputs get switched. In other words, the domain and the ranges of the inverse and the original function also get switched. In other words, my x and my y values also get switched. So if we can switch your x and your y values, then the coordinate pairs that refer to each point get switched as well. Notice that the domain of f is a, b, and c, and the range of f is 1, 2, and 3, but the domain of f inverse is 1, 2, and 3, and the range of f inverse is a, b, and c. So my x and my y values got switched. Let's apply that knowledge to question number 3. If we have a graph of a one-to-one function, then we could graph its inverse function by taking all the points that we know and switching their coordinates. In this first graph, we're given 4 points, and we're going to switch all their x and y coordinates. So notice that I just took the coordinates and I switched the x and the y values. I'm now going to plot them and connect the dots. So here are the points that are plotted, and there is the graph of the inverse function. Let's go ahead and do the second one. We actually don't have very many points given to us for the second function, but we do know that it goes through the points 0, 0, 1, 1, and -1, -1. And any point that falls along the line y equals x has the same coordinates whether or not it gets switched. Take a look at our example from the first question. Even when you switch the order of the coordinates, nothing happens. So those points are going to still be the same, meaning at -1, -1, at 0, 0, and at 1, 1. And the line is basically going to be mirror image if we look at the line y equals x. So tilt your head a little bit and imagine what mirror image would look like. And we'd go like that, we go under, and like that. It's not the best graph, but it's a sketch of what the inverse function would look like. There's a rule about inverse functions, and that's if you compose an inverse function with its original function, you will get the input and the output will be the same. So in this sense, if I originally take x, plug it into my function, and then I take that result and I plug into my inverse function, the result will come back to my original input, x. So for both of these, and it doesn't matter which direction we do first, my input x will yield my output also x. And so if you compose two functions and you think that they might be inverse functions of each other, you can verify algebraically by composing them and seeing that they simplify to beget x. You also want to verify that these functions are inverses by checking their domains and ranges and making sure that the domain of one function is the range of the other. Question 4 asks us to verify that these functions are inverses of each other, and we're going to do that by composing them together and seeing if our inputs and our outputs match up. Recall that we have g as our inner function and f as our outer function, so I'm going to go ahead and write our outer function, replacing the variable with parentheses. So I've written f of x as parentheses minus 2, the whole thing squared, and inside my parentheses I'm going to put my g function, square root of x plus 2. Simplifying this, I get the square root of x plus 2 minus 2 squared, and that's going to cancel out. And then the square root of x squared gives me x. So you can see that my input was x and my output was x. Let's do this again, composing them the other way around. This time g is my outer function, so I'm going to write that first, replacing the variable with parentheses, and then writing my f function inside that parentheses as well. And so notice that I have the square root of x minus 2 squared. The square root and the x minus 2 squared will cancel out, giving me just x minus 2 plus 2, which simplifies to become x. So since I composed g of f of x, and it became x, and f of g of x, and it became x, then I proved algebraically that f and g are inverse functions. Remember, if a question tells you to prove something algebraically, you have to prove that it's true for all values of x. You can't just plug in one value and say it works for that one value. So we have to go through the steps and simplify our x's and simplify our expressions. So for f of g of x, I wrote it as f as the outer function in black, g of x is going to be written in blue inside my function, and I actually have x showing up twice in this expression. I actually have x showing up twice in this function, so I want to plug in g of x twice. And in order to simplify this, I'm going to multiply by the LCD. Multiplying by the LCD in this case will give me the following fraction. Notice that my 1 minus 2x cancels out with the denominators of both of my blue fractions, but gets multiplied by everything else. So the 3x plus 5 is my remainder from that multiplication, and then I have to multiply the minus 5 times the 1 minus 2x. I'm left with a 2 and the numerator 3x plus 5 from the first fraction, and I say plus 3 times the 1 minus 2x. And then let's simplify this. So then the plus 5 and minus 5 will cancel out. The 6x and the minus 6x will cancel out. And then I'm left with 13x over 13, which simplifies down to x. Let's do this again in the other way. Remember that you have to put your inner function in everywhere you see a variable. So that's once in the numerator and once in the denominator, and then we're going to multiply by the LCD of 2x plus 3. You might not be able to see the 2x plus 3 over 2x plus 3 that I wrote on the side, but you can see the results of multiplying. That 2x plus 3 will cancel out with the denominators of each of the orange fractions, and that I will have 3 multiplied by the numerator x minus 5, and then I'm going to get plus 5 times 2x plus 3, and in the denominator I'm going to put 1 times 2x plus 3 minus 2. I'm going to cancel out my 2x plus 3's and be left with x minus 5. Let's rewrite this. And now that I have it all distributed, I know that the minus 15 and the positive 15 will cancel out, and the positive 2x and the negative 2x will cancel out. And so I'm going to be left with 13x over 13, which once again reduces down to x. Recall that your original setup has to show both f of g of x and g of f of x, and that each time they must simplify down to just x. If you're given a one-to-one function, you can find its inverse by following steps 1 through 4. Actually, you would find the inverse function as soon as you switch the x's and the y's. So I like to draw a line between my work so that I know when I'm looking at f and when I'm starting to look at f of x, of f inverse. But the difference is that you don't know the function until you isolate the y. So we do have to take a lot of steps to carefully isolate the y. For question number 6, we're given a function that we're told is 1-to-1. To find its inverse, we're first going to do step 1, rewriting f of x as y equals. At this point, I'm going to switch colors and draw a line, and I'm going to say, let's switch my x's and y's. So I'm going to get x is equal to y cubed plus 1. Technically, this is the inverse function already. It's just not written in function form. So I have to isolate that y. I'm going to do so by subtracting 1 from both sides, and then cube rooting both sides. So I'm left with just y on one side. And I just like to rewrite it so that the y is on the left-hand side, because that's how we're normally used to seeing it. And then I'm going to replace y with f inverse. Now the question says to find the domain and range of these functions. Let's look at the first function. The first function, f of x, was x cubed plus 1. That's a polynomial, and since it's a polynomial, it has a domain of all real numbers. Because it's a cubic polynomial of degree 3, we know that its end behavior goes to positive and negative infinity. So that is going to be the range as well. Both of these facts we learned early in chapter 5. Now let's look at the inverse function. Because we know that inverse functions are related to their original function, we pull the domain from this bit of information. So the domain is going to be all real numbers. We also know that the range is going to come from that information, so we're going to get a range of all real numbers as well. Always, the domain and the ranges of the inverse function are the range and the domain of the original function. For question number 7, we're given a quadratic equation, and it says its domain is x is greater than or equal to 0. I wrote that in interval notation, that our domain is from 0 to infinity, including 0. Now, technically, the domain of this is the same as the domain of a polynomial. It should be all real numbers. Why did we restrict our domain to positives and 0? Let's look at the function real quick. This is the graph of x squared plus 9, and it fails the horizontal line test. This is not a one-to-one function written this way. But let's look at this function on the domain that was given to us. Notice, because they gave us a domain of x is greater than or equal to 0, this function now is 1-to-1, if now passes the horizontal line test. So restricting our domain was really important for getting the function to be 1-to-1. Let's go ahead and go through the steps to find its inverse. Changing f of x to be y, and then drawing a line between our function and its inverse. We're going to switch x is equal to y squared plus 9. And then we want to simplify. So isolate the y. So we're going to put x minus 9 is equal to y squared. I'm going to square root both sides. And technically, when I square root both sides, I get plus or minus x minus 9. Well, that's no good, because that means my y is going to give me two values. And this is because every time we take the square root, we want to put the plus or minus. But in this case, we're just going to take the positive side. We're only going to take the positive side because we ended up taking the positive side here. And so that's how it can match up. I'm going to rewrite it as y is equal to the square root of x minus 9. I'm going to say f inverse of x is the square root of x minus 9. Okay. We found f inverse, but do we know its domain or range? I do know that its range is going to match the domain of f. I'm going to go ahead and write it in algebraic form too, just so we know. If you're going to write it algebraically, you have to use y and not x. For our domain, we were given that it was x is greater than or equal to 0. But for our range, we're going to be given that it's y is greater than or equal to 0 because it's the range values that we're talking about. To find the domain of f inverse, we know that the rule for this is that radicals must be positive or 0 inside the radical. So I know that the x minus 9 must be greater than or equal to 0. That means x has to be greater than or equal to 9. So my domain is going to be from 9 to infinity. Because I found my domain of my f inverse, that's going to give me my range of my f, meaning from 9 to infinity. Now once again, I could write this in algebraic form instead of interval notation, but I would have to say y is greater than or equal to 9, not the x that we have over there. So take care when you're writing your domain and ranges that you're using the correct variable for it. For question number 8, we're given a rational function, and therefore we should know that its denominator cannot be equal to 0. So I'm going to say x plus 4 cannot be equal to 0, so x cannot be equal to negative 4. And that's a really good way to write our domain. I prefer that inequality versus interval notation. To find our inverse function, we're going to say y is equal to, and then when I switch, I have to put y is x, and I have to switch both x's to now become y's. And the steps to isolate y is a little bit harder when you have two y's. So what we're going to do first is multiply both sides by that LCD. So I'm going to get x times y plus 4, and then I'm going to get 2y minus 3. Let's distribute that out. You get xy plus 4x, get 2y minus 3. I'm going to subtract 2y from both sides. I'm also going to subtract 4x from both sides, and I'm going to end up with xy minus 2y is equal to negative 4x minus 3. Now that's because you always have to move all your y terms over to the same side, and then move all your non-y terms over to the other side. We're going to now factor out that y, and we're left with x minus 2 and negative 4x minus 3. I'm going to divide both sides, and I get negative 4x minus 3 over
x minus 2. And the last step you have to do is just make sure you write it in function inverse notation. So don't leave it as y, leave it as f inverse of x. So there's your function. Now this domain of this function is also going to be the denominator is not equal to 0. So then I'm going to get x is not equal to positive 2. That's my domain. Because I found the domain of my f inverse, that's going to tell me that the range of f is y is not equal to 2. I'm grabbing that information from the domain of the f inverse. And because I originally found the original domain that x is not equal to negative 4, that tells me that my range is y is not equal to negative 4. And so my domain and ranges for my f and my f inverse get switched. There's a lot of steps going on in here. You want to practice that so that you can learn how to isolate your y. This is a probable test question, which is similar to number 8. So make sure you practice that. Thank you very much and have a good day.